You're falling toward a black hole. 1 second until you cross the point of no return. Someone watching from a safe distance sees you slow down. To them, your image reddens and freezes at the boundary. To them, you never cross. But from your side, you cross without noticing anything unusual. 2 people, 1 event, 2 completely contradictory truths. Both are correct. Here's what's actually happening. A black hole is a region where gravity is so extreme that not even light can escape. Its boundary, the event horizon, that's the point of no return. Cross it, and every path in your future points only inward. But the event horizon isn't a wall. There's no marker, no flash, no physical boundary to feel. It's defined entirely by what can and can't send signals to the outside universe. Once you're inside, you're cut off from the rest of the universe. Not by a wall, by the geometry of time itself. To the person watching from outside, the physics of time works against you. As you fall into stronger gravity, your clock slows down relative to theirs. Not metaphorically, measurably, mathematically. At the edge of the horizon, their clocks run infinitely faster than yours. You appear to slow, to redden, to freeze. In their frame, you're still there. You've been at that boundary for the entire remaining lifetime of the universe. But from your side, this is completely invisible. Your clock runs fine. Your experience is continuous. You don't feel the dilation. You just fall. Einstein showed that in free fall, you feel no force. Falling toward a black hole, in true free fall, feels exactly like floating in empty space. At the moment of crossing, there's nothing to detect. No alarm. No flash. No sensation. But there's a significant catch. This only works if the black hole's large enough. A black hole 10 times the sun's mass has an event horizon less than 100 kilometers across. The gravity difference between your head and your feet at that distance is enormous. It would stretch you head to toe and compress you sideways long before you reach the horizon. Physicists call this spaghettification. For a small black hole, you never make it across intact. A supermassive black hole is a different story. The black hole at the center of our galaxy has a horizon spanning millions of kilometers. At that scale, the curvature at the crossing point is gentle. The gravity difference across your body there is negligible. You cross alive, without any sensation of crossing. Everything that follows only applies to the large ones. As you approach, light from the entire universe bends around the black hole, toward you. Normally, you look in one direction and see what's there. Now, light from behind you curves all the way around and reaches your eyes from the front. Stars that were behind you appear overhead. Galaxies that were to your sides compress inward. The sky shrinks into a ring above your head. And the ring keeps shrinking. Below you, the region darkens. The light from above gets more and more intense, hotter, higher energy, compressed. At the moment of crossing, the entire visible universe has compressed into a single point. One point of light, directly above your head. You cross. You're still alive. But you're not free. Inside the horizon, you've got a fixed amount of time remaining. The singularity, the point where all known physics breaks down, lies in your future. For the black hole at the center of our galaxy, that time is roughly 60 seconds. For the largest known black holes, it's about 27 hours. But you can't use that time to turn back. The singularity isn't an obstacle in front of you. It's in your future. Like next Tuesday. You can't avoid next Tuesday by moving sideways. You can't avoid the singularity by moving in any direction in space. The physics has already committed. Here's something physicists found that most people find hard to believe. As you approach the horizon, you can still receive signals from the outside, including signals sent billions of years in the future. A message sent after most stars in the universe have died can still reach you here. Your crossing moment, on any physicist's map of the universe, connects to every future signal from outside. The horizon blocks your signals going out. It doesn't block theirs coming in. One-way door. Everything arrives. Nothing leaves. In 1974, Stephen Hawking showed that black holes aren't perfectly black. They emit radiation, extremely faintly for large black holes. But they do glow. And that discovery created a crisis in physics that's still unresolved today. Here's the problem. Physics has a rule: information can't be truly destroyed. You can compress it, scramble it, hide it beyond recovery. But the record of what something was is always encoded in what it becomes. A black hole appears to break this rule. Everything that falls in, your mass, your momentum, your entire physical record, it all seems to be erased. The radiation that comes back out is pure thermal noise. Like heat from a campfire, that tells you nothing about what burned inside it. If that's true, the universe has broken one of its own rules. And that rule breaking changes what your last second might look like. Because if information can't escape, a smooth crossing is acceptable. The universe doesn't know what you carried in, and that's fine. But most physicists now believe information does escape. And if it does, something has to carry it out. In 2012, a group of physicists worked out the contradiction. For information to escape, each particle leaving the black hole must be paired with what it's carrying out. But a particle can only be fully paired with one thing at a time. If it's paired with the information going out, it can't also be paired with the smooth interior. Something has to give. If information wins, if the universe saves its records, the horizon isn't smooth. Instead of a peaceful crossing, you hit a wall of ultra-high energy radiation. Instant destruction at the boundary. This is the firewall. As of today, it remains unresolved. The greatest physicists in the world disagree about what happens at your last second. We genuinely don't know. The dramatic last second you imagined belongs entirely to the person watching from outside. For you, the crossing is nothing. Two observers. One event. Two contradictory truths. Both correct. At its most extreme, physics tells us, reality is always a story for someone. There's more to uncover. See you next time.